Hi, this is Phil Ferrier, here to give you a quick overview of the streaming pipeline we've put together for Task 2 of the Cloud Computing Capstone. Our solution relies entirely on Apache open source projects, which are, from source to sink, Kafka, Spark Streaming, and Cassandra. We use Kafka to fit in flight records into the streaming pipeline. It allows us to take care of an always difficult problem in a streaming system when the producer and consumer operate at different rates. Thanks to Kafka, we don't even have to worry about buffer overruns and underruns. Next, we use Spark Streaming as our data processing workhorse. The great value of Spark Streaming is that it provides us with a convenient abstraction for distributed in-memory chunks of our dataset, and a well-designed API to apply very common data manipulation operations. Last but not least, we use Cassandra to store not only our analysis results, but temporary state as well, that we can query and update periodically with very low latency, which for DBMS is truly remarkable. For this capstone, the data was extracted from compressed CSV files contained on an EBS drive, out of which we created two datasets, one that contained information about all years, and another one about the year 2008. The first one was used to answer the first 6 data mining questions, and the year 2008 CSV was used to answer the last data mining question. Out of the CSV columns, we only kept the ones that were relevant to the data mining question. We discarded incomplete observations based on that set of columns, and for performance reasons, we created composite keys and collapsed date information. Finally, flat records were injected into the streaming pipeline through simple piping, using CAT to read the CSV files sequentially, PV to experiment with different transfer rates, and the Kafka console producer to generate firehose data on a predefined topic. To answer question 1.1, we generate origin and destination tuples, group by airport key and add values, add the results to our running stats by airport key, find the top 10, upsert the top 10 to Cassandra, and finally drop entries from Cassandra but are no longer in the top 10. To answer question 1.2, we generate tuples with the carrier as a key and arrival delay minutes as value, group by carrier key, count the number of flights and sum the arrival delays, add the results to our running stats by carrier key, find the top 10 by our time arrival performance, upsert the results to Cassandra, and finally drop entries from Cassandra but are no longer in the top 10. To answer question 2.1, we generate tuples with origin and carrier as the composite key and departure delay in minutes as value. We group by composite key, count the number of flights, sum the departure delays. Add the results to our running state by composite key, find the top 10 by on-time departure performance, upsert the results to Cassandra, and finally drop the entries from Cassandra and are no longer in the top 10 of each origin carrier pairs. To answer question 2.2, we generate tuples with origin and destination as a composite key and departure delay in minutes as value. We group by composite key, count the number of flights, sum the departure delays. We add the results to our running state by composite key, find the top 10 by on-time departure performance, upsert the results to Cassandra, and finally drop entries from Cassandra but are no longer in the top 10 of each origin-destination airport pairs. To answer question 2.4, we generate tuples with origin and destination as a composite key and arrival delay in minutes as value. We group them by composite key, count the number of flights, sum the arrival delays. add the results to a running state by composite key, find the top 10 by on-time arrival performance, upsert the results to Cassandra. To answer question 3.2, we relied entirely on Cassandra to store state. Flight records were split between morning and afternoon flights. For each flight, either morning or afternoon, flights were grouped by origin, destination, month, and day of month as a composite key. We would then fetch the results for those composite keys from Cassandra, find the flight with minimum delay between the Cassandra results and our current results, write the best results back to Cassandra. To query the results, a user now needs to query the morning and afternoon flights separately. The added benefit of this approach, beyond performance, is that the user can query for an afternoon flight not only for 2 days later, but any other number of days they might prefer. Here are the Cassandra query results for question 3.2. They're all paired here. This is the morning flight, this is the afternoon flight. You can see by the times here. We've picked up the flights with one of the best on-time arrival performance. 2 days apart, and here's the layover airport.